In this section, we're going to see how a new model for the hydrogen atom led to our understanding that matter also has a wave nature to it. So if we can review what we've seen so far, we saw how blackbody radiation started the idea that light was delivered in quantized packets of energy. The photoelectric effect confirmed this, and of course, Compton scattering also established the fact that light was composed of particles, photons, and these photons carry energy and momentum and have both a particle nature and a wave nature to them. Now, Bohr's model of the hydrogen atom basically set up the idea of turning this idea that the photon had this dual nature on its head. We basically were able to see that not only does the photon have this dual nature, but also all particles, all objects composed of matter also have this dual nature. So it started, first of all, an attempt to understand what are known as Fraunhofer lines. These are absorption lines in the solar spectrum. And the first mathematical pattern that was actually recognized in the hydrogen spectrum, as we'll see. Balmer and Rydberg came up with equations that noticed a mathematical pattern. And then this was taken by Bohr, who worked with Rutherford's planetary model to explain how quantizing the orbits of the electron would lead to the spectral patterns that we saw. So starting with Fraunhofer lines are basically the lines, the absorption lines that we see in the solar spectrum. Some of them are due to chemicals in the solar atmosphere. Some of them are actually due to absorption in the Earth's own atmosphere. But the important lines are really the lines which we see from whatever elements are contained within the sun. So again, 1802, Wollaston discovered these absorption lines in the solar spectrum, and then Fraunhofer characterized these lines and labeled them. Basically, they were labeled with capital and lowercase letters. We've already talked about the H and K line, which is used for measuring Doppler shift in galaxies. Now, here's a look at the solar spectrum greatly expanded, and we can see that some of these lines are darker, some of these lines are less pronounced, and really every element in the periodic table is represented somewhere in these spectral lines. So we use the lines as sort of a fingerprint to identify what elements are present and really how much they are present. Now, with spectral lines, we have to understand how they result. For an emission spectrum, if we take a hot gas, such as sodium, hot vapor, we see these orange street lights. They're becoming less and less common as we replace them with LEDs. But these low-pressure sodium lamps and high-pressure sodium lamps have this very distinct orange color. And this comes from the sodium D lines. And the D line is very, very prominent. It's in the middle of our vision sensitivity. So they're very effective as methods of illumination at night. So we heat up a gas, we heat up a vapor, it is going to glow with very distinct spectral lines, such as the case for sodium, which has these two very bright yellow-orange lines. There's also a red line, there's a blue line, and some violet lines, but sodium is easily identified by these two very bright lines. Now, if I cool this vapor down, but now shine white light, all colors through this cooler gas, I get absorption lines. I get the exact position of dark lines where the light lines in the emission spectrum were present. And the reason why we get these dark lines on the sun is because as we're looking at the atmosphere, there is very dense hot gas below the upper part of the photosphere. And basically, the interior of the sun acts as a black body, so it gives off all colors of light. But as we go higher and higher, we actually run into a gradually cooler and cooler atmosphere. And it's these upper atmospheric layers which will then absorb. It's not that cool, but it's cooler than the interior. It will gradually absorb some of the light as it tries to make its way out. So with the solar spectrum, what we see is a bright black body spectrum, all the colors, and superimposed on that is the cooler outer layers, which are absorbing some of these darker lines. So there became the question as to, what were these lines? I mean, it was understood that every element left its own fingerprint. Helium had its own spectrum, lithium, oxygen. No matter what the element was, it could be identified if you could identify the spectral lines that were present. Now, hydrogen is really the center of our story here because hydrogen was the first spectrum that was actually explained. At least we found a mathematical pattern to it, and then we explained it. So the hydrogen spectrum has a very prominent red line, a bluish-green line, and a few violet lines. The red line is a very famous hydrogen alpha line. And oftentimes we will filter out all different colors of the sun, except for the hydrogen alpha line, to see features near the surface of the sun, especially the chromosphere, which we'll talk about in a little bit. The hydrogen beta line, as we said, is sort of a blue-green. And then there is a hydrogen gamma and delta line and some other lines that are here. So these lines give the chromosphere, the region right above the sun's surface, its very distinct color. So if I were to run electricity through hydrogen, I would see this pink, or I guess more properly magenta color. And this is due to the red, blue, and violet emissions. Basically, we consider magenta to be the absence of green, and we have red, blue, and violet, getting pretty close to magenta right there. But again, during a solar eclipse, we can actually see the chromosphere, and the chromosphere is very different from what we normally see when we look at the sun. When we're looking at the sun, we are seeing the dominant surface, the dominant upper part of the dense atmosphere called the photosphere. And this is where most of the light comes from, and it's going to wash out all the other different parts of the atmosphere. The chromosphere, which is right below the corona, if you've ever seen a total solar eclipse, it's really an incredible experience. But the chromosphere is just above the photosphere, and it's barely visible during a solar eclipse, and it has this beautiful magenta color, again, caused by this red, blue, and violet light. So Johann Balmer, in the late 19th century, found a mathematical pattern behind this hydrogen spectrum, and it's known as the Balmer formula. And what he found is that if you looked at the reciprocal of the wavelength, you could take 1/4, 1/2 squared. We'll see why we write it as 2 squared in a bit. If we subtract off some integer, higher than 2, 3, 4, 5, and continuing to infinity, there was a spectral line that would fit this formula. And again, the hydrogen alpha line, the red line, would be n equals 3. The hydrogen beta line would be n equals 4. Hydrogen gamma, n equals 5. Hydrogen delta, n equals 6. And Balmer didn't understand why. He just was able to notice this pattern. And oftentimes, when we're studying something, the recognition of a pattern and applying a mathematical formula to it, or finding a mathematical pattern, is the very beginning to what eventually leads to our understanding. Johannes Rydberg worked on atomic spectra, and he came up with a similar relationship, but it was more general. He worked with hydrogen and alkali metals, and when he looked at atoms with a single electron, or ions with a single electron. So for instance, hydrogen would have 1 electron. First ionized helium would have 1 electron. Doubly ionized lithium would have 1 electron. He noticed the same pattern. For hydrogen, his formula more generalized what was seen, and basically it introduced the concept that we don't just have an integer 2 to the second. This m here can be 1, 2, 3, 4, and so on, leading to other possible spectra. So for instance, the Lyman series, discovered in 1906 by Theodore Lyman, was not as obvious as the Balmer series. It was well up into the ultraviolet light and was difficult to observe. You weren't going to see it in or the sun's spectra, because this ultraviolet light doesn't make it through our atmosphere. So this had to be observed using special laboratory equipment. And I'm not even sure whether at these short wavelengths this would even penetrate normal glass. So this would have to be done with fused quartz, most likely, but I'm speculating. But he observed these ultraviolet spectral lines, and over the next 8 years characterized them, basically finding this condition m equals 1. So again, this spectral line here, this is known as the Lyman alpha, okay? So this would be 1 divided by 1 squared minus 1 over 2 squared. Remember, n has to be greater than m. This would be Lyman alpha. This would be Lyman beta. That would be the n equals 3. Lyman gamma, n equals 4. Lyman delta, n equals 5. And again, it continues on as the lines get closer and closer to one another for higher and higher values of n. On the other side of the spectrum, if we, instead of going to 1, we go to 3, we come to the PASCHEN series. And this was discovered by Friedrich Paschen, and by inserting 3 in here, we again get these different spectral lines. Now, in this case, this would be the Paschen alpha, beta, gamma, delta, and so on. So what was the source of these different lines, the Balmer series, the Lyman series, and the Paschen series? In fact, other transitions were actually found eventually in the infrared. Well, the story continues with Ernest Rutherford. Now, just a little background here. We're going to step back in terms of looking at the classical picture of the atom. In 1909, Hans Geiger and Ernest Rutherford took a gold film, bombarded them with alpha particles, and discovered that the atom actually had a very dense nucleus and it was surrounded by electrons. So they came up with basically what was a model very similar to our solar system, that most of the positive charge was in the center. That's why when they looked at the alpha particles, some being scattered at very, very large angles, that was indicative of a a very small, dense charged object at the center, and that, the electrons would orbit this, much like the planets would orbit the sun. This had many appealing features to it. It was we look at the electric force, it's an inverse square law. Gravity's an inverse square law. It basically had a very, high mass object at the center and much lower mass objects orbiting it. The big problem, however, is in the classical picture, this is not stable. Now, planets will orbit the sun in fairly stable orbits because, as they go around the sun, they're not really giving up any energy. Maybe a really, really small amount of gravitational energy, maybe passing through the interstellar medium. Essentially, there's no energy being lost. That's not true with the electron. For an electron, if it did orbit the nucleus, okay, it would be in a circular orbit undergoing centripetal acceleration. And in E&M, anytime we accelerate a charge, it is going to give off electromagnetic waves, okay? So these electrons should not have been able to orbit the nucleus in stable orbits. Shouldn't have been possible. They should be basically giving up their energy and crashing into the nucleus, and that would be a catastrophe because the entire atom would collapse. So Niels Bohr, who was born in 1885 in Denmark, moves to Cambridge to work with J.J. Thomson. And as the story goes, this was not a great pairing. Bohr did not get along with Thomson, who was his supervisor, and Bohr quickly moved to Rutherford's lab, which was really fortuitous because this led to his discovery. Rutherford had discovered this, or basically had changed the model of the atom to this orbital model. And here is Bohr, who moves to his lab and begins to work on this. So Bohr tries to merge these two ideas, the Rutherford model, which Geiger and Rutherford had discovered the evidence for, and the Rydberg and Balmer discoveries of this mathematical pattern. So he basically came up with some rules here. The first rule, of course, was yes, the electrons are still orbiting the nucleus in circular orbits. We're not changing Rutherford model there. But here's where he does a little bit of an ad hoc correction. He says that only certain orbits are available to the electrons rather than limitless continuous orbits. And the reason why he had to do this is the spectral lines seem to indicate discrete jumps in energy. And again, very similar to trains on a track that you've got to stay on the track until they come to a place where they can switch to another track. But Bohr's model basically said there are only certain orbits that are allowed. And this, of course, would mean that the electron couldn't continuously give up its energy and spiral toward the center. He didn't say why this happened exactly. He gave somewhat of an explanation, and that was that only discrete values of angular momentum would be allowed, where the angular momentum, the orbital angular momentum of the electron would go by its mass, r cross v, where L the magnitude could only be equal to n times this constant right here. Now, this looks like the Planck's constant. It's actually the Heisenberg constant, and it's related to Planck's constant by 2 pi. But again, the electrons could only take up these values, these discrete values, and the lowest orbital angular momentum would correspond to the electron orbiting closest to the nucleus. Then at twice that momentum, the orbit would be out here, 3 times the momentum, so on and so forth. So all of these were quantized. This led to this concept of the Bohr radius, which was that the radius of this orbit had to correspond to a balance of our centripetal force with our Coulomb force. If we set these two equal to one another and impose our restriction for orbital angular momentum, we get that each orbit has a radius equal to n squared, h bar squared over mass, the electrostatic constant, times the elementary charge squared. So the Bohr radius would be roughly about 5 times 10 to the minus 11 meters when we do this calculation. Now, here's where we've got to be careful with Bohr's model. Bohr didn't necessarily believe in this quantized light in terms of that light was composed of particles or photons. He believed that an electron can only absorb a quantity of energy, of light energy, which would be equal to the energy needed to go from one energy level to another energy level. So, for instance, the absorption lines would correspond to light at a particular wavelength, which would allow the electron to jump from a lower orbit to an upper orbit. Likewise, in the emission of light, that would correspond to the electron dropping to a lower orbit, and only certain amounts would be available to the electron in terms of the transitions that it can make. So when we look at the energy of each of these orbits, again, we can go back to our equation for the radius of the orbit. We will essentially combine that with our kinetic energy, our potential energy. When all are considered, the total energy of an electron in this orbit is equal to the kinetic energy plus the potential energy. It's well known that for circular orbits, the kinetic energy is 1/2 the negative of the potential energy. But in any case, when we solve for this, we get essentially that the energy is negative 13.6 electron volts divided by the, we're going to introduce this concept of principal quantum number. That's not just an integer, the principal quantum number n squared. So going back to the hydrogen spectrum, going back to the Balmer spectrum, we saw this red line, this blue line, these violet lines. We get them because we have an electron in this third level right here, okay? And it drops down to the second level. That produces your hydrogen alpha. That corresponds to the smallest energy jump. So that is, with the smallest energy transition, the lowest energy, and thus that represents the longest wavelength. So n equals 4 down to n equals 2 gives us the hydrogen beta, n equals 5 to 2, gamma, then delta is 6 to 2, and then you have many other lines that are here beyond this. This 397 line would be from n equals 7 down to n equals 2. So again, in the Bohr model, the Balmer lines were produced by electrons dropping down to the n equals 2 level. The Lyman series, which was in the ultraviolet light part of the spectrum, corresponded to a much bigger jump. If we remember, the energy goes by 1 over n squared. So the energy difference between n1 and n2 is huge, okay? And therefore, dropping down into the lowest energy state would result in producing an ultraviolet line. So n equals 2 to n equals 1 was the Lyman alpha. Then you have the beta, gamma, delta, so on and so forth, right? If you want smaller energy changes, you would drop to a higher level. Okay, sounds sort of counterintuitive, but think about this. If we're dropping down to the n equals 3 level, these energy drops are very, very small. So they correspond to light in the infrared. So, we look at Bohr's model of the atom, and what we see is that it actually does converge to our classical limit. Bohr's correspondence principle states that the quantum mechanics has to agree with classical physics when the energy difference between quantized levels are very, very small. As our orbits are actually getting, much, much bigger. And let's go back to the radius of the orbit. See how this radius goes by n squared, okay? So your lowest state, the n equals 1, is the smallest. The radius for the next will be 4 times larger. The radius for the next will be 9 times larger. So these orbits are really getting quite large. So at very high ends, essentially, the electron acts very, very classically, okay? In that it's very easy for it to change from an upper level to a lower level. The difference in energy is very, very small compared to the difference in angular momentum, which is the quantized quantity here. So really, with these very, very high levels, they're looking more and more classical until we get to the zero energy level, which is essentially the electron breaking free. So Niels Bohr, as a consequence of his work, receives the Nobel Prize in 1922, and so many of these people who worked on quantum mechanics in the early years received Nobel Prizes as a result. He headed the institute in Copenhagen, again, participated in a lot of the development of early quantum mechanics. But his work was so important to eventually leading to the understanding. Now, he didn't get this initially, but what was happening by quantizing the angular momentum, we were actually restricting the electron to orbit around if you can say it's an orbit, but to orbit around the nucleus in as standing waves. Okay, there were modifications made to Bohr's model, just like it's interesting how there's a symmetry to history in science. If you remember, it was Copernicus and Galileo who said the planetary orbits were circular, and it was Kepler who came along and said, no, they can have some eccentricity to them. They can be somewhat elliptical. Well, in 1913, Arthur Sommerfeld introduced this concept of, hey, why can't the electrons also have elliptical orbits? And this is going to produce our next quantum number. In fact, we know, studying chemistry, that we have a principal quantum number, which is n is equal to 1, 2, 3, 4, and so forth. But we also know that there's another additional quantum number, L, which is related to, in the classical picture, the eccentricity of the orbit. So for instance, for the n equals 1, we can only have an L equals 0. L is always equal to 0 up to n minus 1. N equals 2, we can have L equals 0, L equals 1, N equals 3, 0, 1, and 2 for L, and so forth and so on. We recognize these as the S, the P, the D, and for L equals 3, the F orbitals. Okay? Now, this is not reality. Okay? A better picture of what is happening is, this is a very classical view still. We're still having these particles go around here, is that, in fact, the electrons are waves, they're standing waves, and that this old quantum theory was eventually replaced with a new quantum theory, which is essentially looking at the hydrogen orbiting the nucleus as a three-dimensional standing wave. Okay, so again, this principal quantum number came from Bohr restricting the angular momentum. The L came from Sommerfeld introducing the idea of elliptical orbits, and then later on, we are going to see how solving the wave equation leads to this orbital magnetic quantum number. And then later on, the spin of the electron is going to result in an additional quantum number, spin up, spin down, for the electron. So again, this is the transition that we're beginning to make from treating particles, I should say, treating matter as, you know, completely a particle. And we're going to see how Bohr's model is further refined to include the concept of, you know, particles being waves.